The last calorimetry lab we're going to do is to find the enthalpy of a solution for a salt. And this is a little bit different than the other enthalpy problems we've done, because when we have a solid salt and we dissolve it in water, it dissociates and actually becomes part of the solution. The water's kind of gone. We have this new thing called a solution. So dissociation strikes again. When we put this in here, that solid salt dissociates and it changes the properties just a little bit of the water. To complicate things as well, when we put these in here, there's a heat transfer. So the heat, it's not the water anymore, it's the solution. The heat of the solution is going to be equal to the heat of the salt that was dissociated. Okay, so this is our calorimetry setup. So complicated again, when we say heat of solution, we really mean the heat of the salt, even though the solution over here is a little different. This is our surroundings. So what we're really after at the end, when we call it a heat of solution, is the heat of the salt over the moles of the salt, because that's going to give us kilojoules per mole. So this is the end goal at the end. Now, our solution here, since the water is part of our solution, we have to take some measurements to get the heat of our solution. This solution is very similar to what we've done because it's water-based. We just have the solid salt in it. We put that in and it dissociates. But we take a temperature change of the solution. That's easy enough with a thermometer. The specific heat of the solution is actually still equal to the specific heat of the water. It's close enough that the water is not going to disrupt that value, so we still pretend it's a 4.18 and it's a close enough approximation not to matter. So those two are pretty easy. The real problem here is the mass of the solution, because we can no longer say it's just water. And this is the tricky part when you have solutions. The salt is both part of the system and the surroundings. It's part of the system because it is absorbing or giving off heat in order to dissociate. And then it's part of the surroundings because after it's dissociated, it has to heat up or cool down with the water. So the mass of my solution is now the mass of the water and the mass of the salt. It's both. This will get us our MCAT of the solution, which is our surroundings. That's the water. And the salt is our system. So we change the sign and we know if this one absorbed heat, this one gave it off, and vice versa. And then we can use the heat of the salt to calculate the enthalpy of that salt. And this is confusing because we're talking about the system, we're talking about the heat needed to make a solution, which is the dissociation part, but we're not using that word solution the same way as we have over here for the surroundings, because here we're just using the solution to measure the heat transfer, the MCAT equation of the solution that we made. But really we're talking about the heat needed to dissolve this thing, which is the system. So there's some vocab that gets thrown around kind of recklessly in this area, including the mass of the water and the salt together in the surroundings is the main idea here. And then you will also, when we're actually talking about the salt itself, you will need the mass of the salt just isolated by itself in order to get the moles of the salt, and you can solve for the enthalpy in either kilojoules per mole or kilojoules per gram, depending on your salt.